Today I'll be talking about two-tailed hypothesis testing for a regression coefficient. Once you get regression output, either from Excel or maybe it's just provided in the problem instead of the raw data, you're often asked to do a hypothesis test on the coefficients. So why do we do hypothesis testing, and what are the steps to running a hypothesis test? Well, the primary reason that we use hypothesis testing is to determine if the variables we used as predictors are actually useful at all in predicting the dependent variable. I'll talk about that a bit more in detail in a moment. As to what the steps are, well, there are 5 steps to a hypothesis test, though you might see them in other tutorials broken up into more steps or combined into less steps. The first step is to determine your hypotheses and the interpretations of those hypotheses. The second step is to determine alpha, which is the level of significance, and the degrees of freedom. The third and fourth steps kind of go together, and those are calculating the test statistic and the p-value. And finally, in the fifth step, we draw a conclusion from comparing the p-value to alpha and interpreting that conclusion. Like I said previously, we primarily use hypothesis testing to determine if the predictor variables we've used are actually useful. That is, if they're actually helping to predict the dependent variable. So the most frequent hypothesis test you'll use is a test for 0, as we see on the left. In hypothesis testing, we always have 2 and only 2 hypotheses. The first is called the null hypothesis, and the second is called the alternative or alternate hypothesis. You can also think of the null hypothesis as the default. So let's talk a little bit about this fancy Greek b, which we call beta. Beta represents the true value of the coefficient, and that's something that we don't know because a regression is typically run from sample data, not population data. A sample is an imperfect representation of a population, so that when we get regression output, that output is also an imperfect representation. Specifically, the regression output is going to contain sample coefficients, which we'll denote with lowercase b's, and you'll see that when we talk about constructing the test statistic. For the moment though, just realize that beta is something that we don't know, and we're going to run a test to see what it's likely to be. So in the first type of test, the test for 0, what we are trying to do is see if the variable is useful. If the true coefficient beta is 0, that means that the slope associated with that variable is 0. So if you look down to where the graphs are drawn, you can see that a slope of 0 means that there's no relationship between the x and y variables. Different values of x don't help predict the value of y. In this context, this relationship, or lack thereof, will be referred to as a linear relationship. So just be aware that the term linear relationship refers to either a positive or negative association between the variables, like you see in the lower 2 graphs. The second type of a two-tailed hypothesis test is a test for a specific number, and the interpretation of this is a little easier. The null hypothesis interpretation is just that beta, or the slope coefficient, is a specific number, while the alternate interpretation is that the slope is not that specific number, or that it's different from the specified number. You'll see this test a decent bit, so make sure that you know how to interpret both types of tests. Now on to step 2, which is much more straightforward than the hypothesis interpretations. Step 2 is to determine alpha, the level of significance, and the degrees of freedom. Most times alpha will be given to you in the problem, but otherwise the default value, at least in most statistics classes, is 0.05. Other common levels of alpha are 0.01 and 0.1. Just to give you a bit more information on alpha, this significance level is basically the error that we'll tolerate in potentially rejecting the null hypothesis when it is actually true. So if alpha is 0.05, what that means is that we have a 5% risk of rejecting the null hypothesis when it is actually true. That might sound bad, but the issue with hypothesis testing is that we can never quite be sure we're right because we'll never actually know beta. So hypothesis testing lets us at least know the error that we might have in making our conclusion. Now, as far as the degrees of freedom go, this is also pretty simple, even though we may have to do a small calculation. The degrees of freedom for a t-test, which is the type of test that we use for hypothesis testing of regression coefficients, is n minus k minus 1, where n is the number of data points or observations that we have, and k is the number of predictor variables that we've used in our regression model. If you have the full regression output, including the ANOVA table though, you can just find the degrees of freedom in the cell for the residual degrees of freedom, which is n minus k minus 1, already calculated. Now on to steps 3 and 4. This is where we get the mathy part of the hypothesis test, but bear with me. It's easier to talk about these two steps together because step 4 uses the test statistic that we calculate in step 3. So first, we see the actual equation for calculating a test statistic, which is t equals b minus beta over s sub b. Those little black numbers just represent the subscripts that would indicate which variable we're concerning ourselves with. For example, a 0 indicates the intercept row, a 1 would indicate the first variable, a 2 the second, and so on. B, remember, is the sample coefficient that we get from our regression output, and then SB, or S sub B, is the notation for the standard error, which we haven't really talked about, but all you need to know for the purpose of hypothesis testing is that it is shown next to the coefficients column in the regression output. Finally, beta, which we discussed earlier, is that population coefficient that is unknown, but what we're going to do here is take the value that we assumed beta to be from our null hypothesis. I highly suggest doing this calculation in Excel to avoid rounding error, and then labeling the resulting value as the test statistic. So now that we have our test statistic, we need to get what's called a p-value, which is the probability of obtaining test results at least as extreme as the results that we actually observed, assuming that the null hypothesis is correct. An easier way to think of this is how likely our data is to have occurred if the null were true. To obtain the p-value, we use the t-distribution command in Excel, which is t.dist. This command has 3 inputs. The first is the test statistic value. The second is the degrees of freedom. Remember that we got this back in step 2. And then the third input is just true in all capital letters. The word true just tells Excel that we want the probability to the left of our statistic value and not just at the statistic value. So we already have these 3 parts, so this step should be super easy, right? Not quite. This is the step that I see a lot of students mess up on because of how distributions actually work. As you can see with the drawing to the lower right, the t-distribution is symmetric with 2 tails. We're running what's called a 2-tailed test, which we know because the alternate hypothesis had a do not equal sign instead of a greater than or less than sign. Excel is a bit dense and thinks that we only want the probability to the left of our test statistic value, but we have 2 tails. So what we have to recognize is that we need to ask Excel for the left tail, and then we can just double that to get both tails, since this distribution is perfectly symmetric. But how do we make sure we get the left tail? Well, we have to use the negative t-value to tell Excel, hey, we just want what's to the left of this negative value. If we use the positive value, Excel will give us not just the left tail, but everything in the middle too, which is not what we want. So if the test statistic we got in step 3 is negative, that's great. We can just stick it into this t.dist function, no problems. But if our test statistic came out to be positive, well, that just won't work. And we need to make that test statistic negative. The easiest way to do this is just to stick a negative in front of the cell reference to the cell that contains the statistic calculation. But again, that negative value only provides the left-hand tail probability, so then we need to double that to include the right-hand tail as well. I highly suggest labeling each calculation you do, since you might go through several steps to get to the p-value. For example, you might have a cell with your test statistic, another cell with the degrees of freedom, another with your left-hand tail calculation, and yet another with the total p-value after you double the left-hand tail. These values can get very confusing without labels, so when you go to actually make your conclusion, those labels can be super helpful. So with the p-value calculated, we have one final step, the conclusion. Remember, as I said before, we can think of the p-value as how likely it is for our data to have occurred if the null were true. The default is the null, so unfortunately we can't ever actually prove the null. We simply can't reject it if there's not enough evidence to prove the alternate. This situation is often compared to trial proceedings because the language that is used is guilty and not guilty. Not guilty isn't really innocent, but it means that the court hasn't found the evidence to be strong enough to prove the person guilty. You can't really ever prove a person innocent. Similarly, we can't ever prove the null, so if we don't have enough evidence to reject the null, we simply say, do not reject. So now let's look at how to know when to reject or not reject and what that means in different situations. Everything in hypothesis testing is in terms of the null. So if the p-value is small, it's unlikely that the data would have occurred if the null were true. In this case, we should reject our initial assumption of the null and instead move to the alternate hypothesis and interpret that. Instead, if the p-value is large, it's very likely that the data would have occurred if the null were true. So we should not reject the null. A simple way to remember this is if p is low, HO must go. If p is high, HO survives. Remember that we compare p to alpha, the significance level, to determine whether p is low or high. You might think that a p-value of 0.2 is low, but it is larger than all of the typical values of alpha. So in the context of hypothesis testing, a p-value of 0.2 would be considered high. This little sentence helps us to determine whether to reject or not reject the null. But what's our actual interpretation? Well, if p is low and we reject the null, we would interpret the alternate. Depending on the hypothesis we decided on in step 1, this means that either there is a linear relationship if our test was for 0, or the true coefficient beta is significantly different from the number we assumed it to be. If p is high and HO survives, we want to interpret HO, the null, which means that there isn't a linear relationship if we were testing for 0, or beta is not significantly different from the number that we assumed it to be. You'll only have one interpretation because you can only run one type of test at a time. But I find it easier to lay it out in this manner with the different interpretations and the different potential conclusions so that you can get a sense of the 4 different possible conclusions depending on the type of test and whether or not you'll reject the null. And as long as you understand the steps that we've talked about, you'll do just fine with hypothesis testing. I hope this video helped you better understand the steps to conduct a hypothesis test of a regression coefficient. As you practice the steps, this process will become much quicker for you, and so don't worry if it takes a lot of thought right now. With more practice, you can become a pro at hypothesis testing. Thanks for watching.